NASA has confirmed what many suspected. Its Mars orbiter successfully captured extraordinary images of interstellar visitor 3I/Atlas. Meanwhile, China has already shared a complete 302-frame sequence with the world. Yet NASA's high-resolution shots, potentially the clearest views ever obtained of an object from beyond our solar system, remain trapped behind bureaucratic walls. With planetary defense speculation intensifying and scientists raising urgent concerns, one question looms larger by the day. Why is the most significant space imagery of the year still being withheld? Behind the mounting pressure, deafening silence, and enormous stakes lies a confrontation stranger than anyone anticipated. The confirmation arrived without fanfare. NASA officials publicly acknowledged that the Mars Reconnaissance Orbiter's HiRISE camera successfully photographed interstellar object 3I/Atlas during its close Mars encounter on October 3, 2025. These images are authentic, documented, and now part of the official record. For the first time in human history, a spacecraft orbiting another world has turned its most sophisticated camera toward a visitor from interstellar space, an astronomical achievement of profound significance. Yet while China's Tianwen 1 probe has already released its complete 302-frame observational sequence, NASA's superior imagery remains locked in digital vaults, inaccessible to both public observers and the international scientific establishment. As news of the data embargo spread, questions proliferated exponentially. NASA's official explanation centers on procedure. The U.S. government shutdown, which commenced on October 1st, forced a suspension of virtually all non-essential operations, including the processing and public release of scientific datasets. Federal law dictates that only activities directly related to spacecraft health and mission-critical safety can continue during such closures. The HiRISE data, though securely archived, cannot progress through the standard sequence of calibration, validation, and public dissemination. For weeks, the world has waited while these images sit dormant in NASA's processing pipeline. Transparency has emerged as a central issue as competing space agencies and international observers watch China rapidly fill the information void. The China National Space Administration moved decisively, releasing its own Mars orbiter imagery of 3I/Atlas showing a luminous, compact coma, a brilliant point of light wrapped in a faint halo, captured from approximately the same distance as NASA's planned observations. Though the Chinese images possess lower resolution than what HiRISE can potentially deliver, their swift publication highlighted a stark contrast in institutional transparency and operational speed. Speculation about a planetary defense alert has circulated widely across online platforms and certain media channels. However, NASA has issued no official warning nor elevated any threat assessment concerning 3I/Atlas. The agency's public communications consistently emphasize that the object presents zero risk to Earth and that scientific discovery remains the sole focus. The so-called Maximum Planetary Defense Alert appears entirely unsubstantiated, driven more by speculation and conjecture than by any documented action from NASA's Planetary Defense Coordination Office. Nevertheless, pressure continues building from multiple directions. U.S. Representative Anna Paulina Luna has stated publicly and unequivocally that NASA will release the HiRISE images once the government resumes normal operations and completes necessary internal reviews. Harvard astrophysicist Avi Loeb has distributed open letters throughout the scientific community, arguing forcefully that scientific progress depends fundamentally on timely access to new observational data, particularly when anomalies might challenge long-established theoretical frameworks. For now, the images remain under institutional lock and key, their contents known only to a small circle of mission personnel. The world waits as the stakes, scientific, political, and public, continue climbing. The infrastructure supporting NASA's scientific data pipeline operates on principles of precision, established routine, and strict legal compliance. When the U.S. government shutdown began at midnight on October 1st, 2025, nearly every non-essential NASA operation was mandated to cease immediately. This was not discretionary or subject to internal policy modification. The shutdown triggered federal statutes requiring that only activities necessary for the immediate protection of life, property, or national security could continue. For the Mars Reconnaissance Orbiter's HiRISE camera, this meant the spacecraft itself remained under continuous monitoring to ensure operational health and safety. But the flow of new scientific data, including the intensely anticipated images of 3I/Atlas, ground completely to a halt. The processing methodology can only be described as painstakingly methodical. After HiRISE captured its scheduled imaging sequences during the comet's close approach on October 2nd and 3rd, 2025, the raw data were stored aboard the orbiter, then downlinked to Earth during routine deep space network communication passes. Under normal circumstances, these files would transfer immediately to the HiRISE Operations Center at the University of Arizona, where civilian technical teams would convert the telemetry, calibrate the images, and conduct comprehensive quality assessments. From there, the science team would review processed datasets, validate results, and prepare materials for public release. Each step is governed by rigorous protocols, and each requires personnel who, during a shutdown, are legally prohibited from working unless specifically exempted. No component of this pipeline, from raw data ingestion through calibration, validation, and final posting to NASA's public archives, was classified as essential work. Waivers permitting exceptions are extraordinarily rare, typically reserved exclusively for matters involving national security or immediate danger, never for routine scientific observation. The only staff authorized to remain active were those responsible for spacecraft safety, not data analysis, not scientific interpretation, and certainly not public engagement. Even the routine review and approval of imagery by NASA's Public Affairs Office was completely frozen. The shutdown's impact extended to public records requests as well. Freedom of Information Act inquiries, which frequently provide access to internal correspondence or mission documentation, face their own mounting backlog. No FOIA release communications regarding the HiRISE 3I/Atlas dataset appeared in NASA's document repositories during this period, and standard response time stretched indefinitely as the shutdown persisted. This procedural freeze is hardly unprecedented. Past government shutdowns in 2013 and 2019 followed identical patterns. Emergency data releases occurred only when legally or safety mandated, never for general scientific interest or public curiosity. Without presidential or congressional override, the regulations are absolute and inflexible. Consequently, the HiRISE images, while safely stored and fully acquired, remain locked in the processing pipeline, untouched by scientists or public observers, until the government could reopen and a complete team could return to their stations. Public pressure intensified as days stretched into weeks without any appearance of the HiRISE imagery. In Washington, Representative Anna Paulina Luna issued an unambiguous statement. NASA would be expected to release the 3I/Atlas images immediately upon government reopening and completion of necessary internal reviews. Her declaration echoed across science journalism outlets and social media platforms, amplifying calls for institutional accountability. Luna's demand transcended mere procedural requests. It signaled that the image blackout had evolved beyond technical delay into territory of public trust and governmental transparency. She framed the controversy as fundamentally about openness, arguing that discoveries of this magnitude belong to humanity collectively, not merely to the handful of officials controlling the data infrastructure. Avi Loeb adopted a distinctly philosophical stance. Beyond congressional chambers, the Harvard astrophysicist, renowned for challenging conventional thinking about interstellar objects, dispatched open letters to NASA leadership and congressional oversight committees. He argued that scientific advancement depends critically on timely access to fresh observational data, especially when evidence might reveal something genuinely unexpected. He wrote, "Science advances by pursuing anomalies that defy established paradigms and by gathering new data. 3I/Atlas represents a gift for discovery. For Loeb, the comet's extended observable trajectory through the solar system constituted a rare opportunity, not just for professional researchers, but for the general public and for students who might be inspired to pose new questions about our universe." Loeb's advocacy extended beyond technical arguments. He drew sharp distinctions between what he termed the humility to learn and the arrogance of expertise. In his perspective, openness represents not merely courtesy, but a fundamental scientific value. He added, "If we truly want to make progress, we must be willing to admit what we don't know and let the evidence guide us forward." His message resonated powerfully among journalists, educators, and citizen scientists who viewed the 3i/Atlas episode as a crucial test of whether major scientific institutions could keep pace with public appetite for discovery. Transparency campaigns multiplied rapidly. Advocacy organizations and science communicators circulated petitions and open appeals urging NASA to publish the imagery at the earliest possible moment. Many observers pointed to China's rapid Tianwen 1 data release as a striking contrast, arguing that United States leadership in space science depends equally on openness and technical excellence. Others warned that prolonged delays could fuel conspiracy theories or progressively erode confidence in the agencies entrusted with stewarding humanity's greatest endeavors. The stakes had transcended internal institutional concerns. The conflict over the HiRISE images now involved lawmakers, scientists, and a global audience invested in the outcome. Each new statement from Representative Luna or from Loeb intensified the perception that what hung in the balance was not merely scientific, but fundamentally civic in nature. The images themselves had transformed into symbols of transparency, of international rivalry, and of the public's right to witness the unfolding narrative of the third confirmed interstellar visitor ever recorded. In this charged atmosphere, every additional day that data remained locked away only sharpened demands for answers and accountability. October 3rd, 2025 presented an observational opportunity without parallel. As 3i/Atlas swept past Mars at a distance of 29 million kilometers, the geometric alignment positioned the interstellar visitor within range of some of humanity's most advanced cameras deployed beyond Earth. For HiRISE, the high-resolution imaging science experiment aboard NASA's Mars Reconnaissance Orbiter, this represented a test of both engineering capabilities and precise timing. The camera features a 50-centimeter aperture paired with a 12-meter focal length, designed to resolve features on a Martian surface smaller than 1 meter across. Yet at distances spanning tens of millions of kilometers, even HiRISE confronts the fundamental limits imposed by physics and distance. The scientific value of this observational window was apparent from the outset. 3i/Atlas stands as only the third object ever confirmed to have entered our solar system from interstellar space. Unlike its predecessors, it would pass sufficiently close to a major planet to permit direct imaging by an orbiting spacecraft. With HiRISE's sophisticated optical system, the objectives were to capture the structural details of the comet's coma, measure its brightness distribution profile, and refine trajectory calculations with unprecedented precision. Each frame offered opportunities to test theoretical models of cometary activity, search for evidence of jets or outbursts, and look for any hint of structure that ground-based telescopes observing from Earth could never resolve. HiRISE's technical advantage was substantial. At Mars distance, the camera could theoretically achieve a pixel scale ranging from approximately 18 to 30 meters per pixel for a target like 3i/Atlas. That resolution is at minimum twice as sharp as what China's Tianwen, one orbiter, could deliver with its 38.7-centimeter high-resolution imaging camera, and vastly superior to the 120 kilometers per pixel scale representing Hubble's best achievable efforts from Earth orbit. In practical terms, HiRISE was the only instrument positioned to capture the comet's inner coma with sufficient clarity to measure brightness profiles accurately and potentially detect subtle asymmetries or fragmentation events. The flyby's timing was no accident. Months of advanced planning went into synchronizing HiRISE's imaging schedule with the comet's closest approach. Mission engineers calculated precise trajectories, accounting for the comet's high velocity and extreme faintness. Exposure times had to remain brief, often less than 1 second, to prevent motion blur, pushing the camera's tracking system to its operational limits. Even under optimal conditions, the faint nucleus of 3i/Atlas would remain unresolved, appearing as an intensely bright point surrounded by a diffuse, compact coma. No instrument currently orbiting Mars or Earth could realistically reveal surface details on the nucleus itself at this distance, but HiRISE could still provide the sharpest available view of the comet's envelope and immediate surroundings. The urgency driving this observational campaign stemmed from the event's extraordinary rarity. Opportunities to image an interstellar object from another planet's orbit are vanishingly uncommon. The resulting data promises not only to refine theoretical models of interstellar comet behavior, but also to establish benchmarks for future missions and international collaborations. As China's Tianwen, one team moved swiftly to release their imagery. The scientific community watched NASA's HiRISE dataset with keen anticipation, understanding that even modest improvements in resolution could unlock transformative insights about the nature and origins of 3I/Atlas. The observational window closed within mere hours, but the questions it raised and the data it produced will shape planetary science for years to come. Tianwen, one moved with remarkable speed following the October 3rd Mars flyby, releasing a complete 302-frame image sequence of 3I/Atlas to the global scientific community. Each frame captures the interstellar object as it appeared from Mars' orbit at roughly 29 million kilometers distance, using the orbiter's high-resolution imaging camera. The result is a time-lapse animation tracking the comet's progress against the darkness of space, frame by sequential frame, as it sweeps past a red planet. The images reveal a compact, intensely luminous core surrounded by a faint diffuse cloud, the classic signature of a comet's coma. Even at this distance and with an aperture of 38.7 centimeters, the nucleus remains unresolved, appearing in each frame as a brilliant white point enveloped by a subtle halo of dust and gas. The sequence provides no hint of surface features or jet structures, but it does permit researchers to measure the coma's brightness profile and estimate its overall extent. Early analyses published by both Chinese and international astronomers confirm the object's point-like appearance and the presence of a broad, symmetric envelope with no obvious indications of fragmentation or outbursts during the imaging window. The Tianwen, one release stands out not merely for its scientific content, but for its timing and institutional transparency. By publishing the entire 302-frame series within days of acquisition, the Chinese mission team enabled astronomers worldwide to examine the data independently, refine orbital calculations, and compare ground-based observations with space-based measurements. The open release also sparked a wave of public engagement. Citizen scientists and student groups began downloading the frames, stacking and processing them to create their own animations, and sharing results across social media platforms and preprint archives. For many participants, this represented their first direct experience working with raw spacecraft data collected from another planet. In the absence of NASA's high-resolution HiRISE images, the Tianwen 1 dataset became the primary resource for studying 3I/Atlas's appearance during its historic encounter with Mars. While the images do not resolve the nucleus or reveal fine structural details, they offer a consistent empirical record of the comet's behavior at a unique vantage point in its interstellar journey. The Chinese team's decision to release the full sequence so rapidly underscored a growing expectation within planetary science that discoveries involving rare, high-profile objects should be shared openly, enabling immediate scrutiny and cross-border collaboration. 9 distinct anomalies have been discussed in connection with 3I/Atlas, each raising questions that remain unresolved in the absence of complete peer-reviewed analysis. Among the most widely cited is a claim of unusually elevated nickel content reported in preliminary spectroscopic data, though not yet confirmed in formal scientific literature. Early readings suggest elevated nickel-to-iron ratios, though experts caution that calibration artifacts or low signal-to-noise levels could potentially explain the results. The object's trajectory, described in certain circles as unexplained, is hyperbolic and entirely consistent with an interstellar origin. However, minor deviations from gravity-only predictions remain within the range of known cometary activity. No published orbital solution has demonstrated genuinely anomalous motion. The coma and tail structure have attracted particular attention. Both Chinese and NASA briefings confirm a compact, bright coma with minimal evidence of jets or filamentary structure. NASA's own statements echo Avi Loeb's early observation of an abnormal tail, but the specifics, whether related to dusty gas composition or unusual brightness profiles, remain unquantified. No images released to date, including those from Tianwen 1, have resolved the nucleus or revealed fine detail. Even when NASA's HiRISE images are eventually released, the technical limitations of orbital cameras at 29 million kilometers mean the nucleus will remain a point source surrounded by a diffuse envelope. The best available data will permit improved measurements of coma size and brightness distribution, but not the kind of surface detail some observers have hoped for. Uncertainties extend to other reported anomalies as well. Claims of unusual rotation periods, early onset of activity, and unexpected reflectivity characteristics are all based on limited or preliminary datasets. Most professional astronomers urge caution, noting that none of these features yet falls demonstrably outside the range of known comet behavior. The process of scientific validation, calibration, peer review, and cross-agency analysis requires substantial time, particularly for rare and distant objects. Looking ahead, the future of interstellar object discovery is poised for dramatic transformation. The Vera C. Rubin Observatory's legacy survey of space and time will soon commence full operations, scanning the southern sky to unprecedented depth every few nights. Upgrades to the Atlas network, with expanded coverage and improved sensitivity, will significantly increase the odds of detecting faint, fast-moving visitors from beyond our solar system. Together, these survey programs are expected to boost the rate of interstellar detections from roughly one every few years to potentially one or two annually. Each new object will arrive with its own constellation of mysteries and opportunities, reinforcing the critical need for open data policies and robust global collaboration. For scientists and the public alike, the story of 3I/Atlas serves as a powerful reminder that the unknown remains the most potent engine for discovery. Right now, the world's highest resolution images of an interstellar visitor remain beyond public reach, not for lack of technological capability, but for lack of institutional transparency. As new survey programs like LSSD prepare to identify more cosmic visitors, public access to discovery becomes a genuine frontier. In a universe growing incrementally less mysterious with each passing year, withholding data is what truly keeps humanity in the dark. The images exist. The technology succeeded. The opportunity was historic. What remains missing is the will to share what has already been seen, to let the world witness, question, and understand together. Until that changes, the greatest discoveries of our age may remain locked away, known to only a privileged few, while the rest of us wait in the darkness, wondering what truths lie just beyond the bureaucratic walls. November 8, 2025, 11:47 p.m. Eastern Standard Time. A single compressed file appeared on an anonymous image board, posted from an untraceable account. The file name, MRO_HiRISE_3IAtlas_raw_October3_full_zip. Within minutes, the 4.2 gigabyte package had been mirrored across dozens of servers worldwide. By dawn, it had reached every major astronomical institution on Earth. The file contained 47 full-resolution HiRISE frames of interstellar object 3I/Atlas. Every image from the October 3rd observational sequence, completely uncalibrated, exactly as they had been downlinked from the Mars Reconnaissance Orbiter. NASA's carefully guarded secret had escaped into the wild. Dr. Sarah Chun was 3 hours into her night shift at the European Southern Observatory when her phone exploded with notifications. She opened the first message from a colleague in Tokyo. "You need to see this. Now." The download took 12 minutes. Her hands trembled as she loaded the first raw frame into her calibration software. What appeared on her screen made her breath catch. The compact coma was there, exactly as the Chinese images had shown. But at HiRISE's superior resolution, something else emerged from the noise, something that should not exist on any natural comet. A pattern, not the chaotic jets and asymmetric outflows typical of cometary activity. This was geometric, structured, a series of faint radial lines extending from the central brightness, evenly spaced at precise 40-degree intervals, creating a ninefold symmetry that screamed artificiality. She processed the second frame. The pattern had rotated exactly 4.44 degrees. Third frame, another 4.44 degrees. A rotation period of 81 seconds, impossibly fast for a natural comet several hundred meters across, yet perfectly consistent across every single frame. Dr. Chen reached for her phone with shaking hands and began making calls. Within the hour, 14 separate research groups across 4 continents had independently confirmed her findings. The structure was real. By 6 a.m., the International Astronomical Union had convened an emergency virtual session. Over 300 astronomers joined the call, many still in pajamas, all staring at the same impossible images. Dr. Raj Patel from MIT's Kavli Institute spoke first, his voice tight with controlled excitement. I've run every spectral analysis tool we have. The 9 radio features showed distinct emission signatures, not reflected sunlight, but active emission. The wavelengths matched nothing in our catalogs of known cometary compounds. There's more, interrupted Dr. Elena Volkov from Moscow Space Research Institute. I've been comparing the rotation rate against the object's estimated mass based on brightness. The centrifugal force at the equator would be approximately 2.3 times what's needed to overcome gravitational binding. If this were a natural rubble pile, it should be flying apart. Something is holding it together. Avi Loeb's face appeared in the video window, his expression unreadable. Ladies and gentlemen, I believe we need to consider the possibility we've been reluctant to voice. The structural symmetry, the anomalous rotation, the emission signatures, the excessive nickel content. Individually, each could be explained away. Together, they form a coherent pattern. He paused, letting the weight of his next word settle. We may be looking at our first confirmed techno-signature. The chat exploded with reactions, skepticism, excitement, demands for more data. But beneath the professional discourse ran an electric current of realization. Everything had just changed. At 9:17 a.m., NASA's administrator issued a brief statement confirming that unauthorized access to preliminary, uncalibrated scientific data had occurred. A formal investigation was underway. The agency emphasized that raw data requires extensive validation before any scientific conclusions could be drawn. But the careful bureaucratic language couldn't contain what was already spreading across the globe. By noon, the hashtag #FirstContact was trending worldwide. News networks ran continuous coverage. Amateur astronomers pointed every telescope they owned at the comet's current position, now receding past Jupiter's orbit. Representative Anna Paulina Luna called an immediate press conference. For weeks, I've been demanding transparency. Now we know why NASA was so reluctant. The American people, the entire world, deserves to know what we found. This is not a matter of national security. This is a matter of human destiny. As more researchers processed the leaked data, additional details emerged that deepened the mystery. The coma wasn't uniform dust and gas. Spectroscopic analysis revealed it consisted of distinct shells, 7 concentric layers, each with slightly different compositions, each separated by exactly 147 kilometers. The nickel anomaly was a measurement error. Multiple independent analyses confirmed nickel concentrations 340 times higher than any known solar system comet, with an isotopic ratio that didn't match any stellar nucleosynthesis model. Most striking, buried in the metadata of frames 23 through 31. During a brief period when the object's orientation changed relative to HiRISE, a team at Cambridge detected what appeared to be regular geometric features on the nucleus itself, straight edges and right angles that no natural formation process could produce. On November 10th, at 4 p.m. Eastern Standard Time, NASA held a full press conference, not to apologize for the leak, but to present their complete analysis. The administrator stepped to the podium, flanked by senior scientists and, notably, several members of the Department of Defense. 3 weeks ago, the Mars Reconnaissance Orbiter successfully imaged interstellar Object 3 I/Atlas. What we discovered required careful analysis and verification before we could responsibly share it with the world. The leak forced our hand, but I'm grateful we can now speak openly. Behind him, a massive screen displayed the process HiRISE images in stunning clarity. 3 I/Atlas is not a natural comet. We believe it to be an artificial structure, a probe or vessel from another civilization, traveling through our solar system. The geometric patterns you see are consistent with some form of propulsion or attitude control system. The shells in the coma appear to be stage detective layers, possibly ablative shielding designed to survive the journey through interstellar space. The room erupted. He raised his hand for silence. We don't know who built it. We don't know its purpose. We don't know if it's operational or a derelict. What we do know is that it came from beyond our solar system. It possesses clear signs of intelligent design, and it passed within observing distance of Mars precisely when our most advanced camera could image it. He paused, his next words measured and grave. Some of my colleagues believe that timing may not be coincidental. 3I/Atlas's trajectory, while hyperbolic, brought it through the inner solar system at a velocity and angle that maximized its observability. If it is indeed a probe, it may have wanted to be seen. As the world reeled from NASA's confirmation, radio astronomers at the Very Large Array in New Mexico detected something that had been there all along, hidden in data they collected weeks earlier but never fully processed. A repeating signal, incredibly faint, emanating from 3I/Atlas's position. Not random noise, not natural emissions. A sequence of 1,679 pulses, a semi-prime number, the same mathematical principle used in the famous Arecibo message humanity had sent to the stars in 1974. When arranged as a 23 by 73 grid, the pulses formed an image, a star map showing 9 stellar systems, with one highlighted, a red dwarf 47 light-years away in the constellation Eridanus. At the bottom of the image, a simple diagram, a trajectory line showing an object leaving that star system, traveling for thousands of years, passing through ours, and continuing onward. 3I/Atlas wasn't here to stop. It wasn't here to invade or make contact. It was here to say hello in passing, one civilization's message to any others that might be watching, proof that somewhere out there, across the vast darkness, we are not alone. The probe was already past Jupiter, accelerating on its journey to whatever lay beyond. In a few months, it would cross the heliopause and return to the interstellar void, carrying its secrets deeper into the cosmos. But it had left us something irreversible. The knowledge that intelligence exists beyond Earth, that it builds and explores and reaches out across the stars. In the weeks that followed, the world transformed. Funding for space programs increased 20-fold. International cooperation reached unprecedented levels as nations pooled resources to launch an emergency mission to intercept 3I/Atlas before it escaped the solar system, a desperate attempt to learn more, to perhaps send our own message back. Universities overflowed with students pursuing astronomy, physics, engineering. Humanity had glimpsed its cosmic context and found it electrifying. The bureaucratic walls that had kept the discovery hidden became a cautionary tale. Representative Luna introduced legislation requiring immediate public release of any data bearing on the question of extraterrestrial intelligence, ensuring no future discoveries would face the same delays. Avi Loeb stood vindicated, though he took no satisfaction in being right. "This isn't about me," he told reporters. "It's about what we do next. We've been found. We've been measured. Now we must decide what kind of civilization we want to be, one that hides from the universe, or one that steps forward to meet it." The HiRISE images, once locked behind bureaucratic walls, now hung in museums, appeared in textbooks, inspired children's dreams worldwide. They had become humanity's most important photographs, not for what they showed, but for what they proved. Somewhere in the darkness between stars, 3I/Atlas continued its ancient journey, carrying news of a young species that had finally learned to look up and understand what it was seeing. The age of isolation had ended. The age of reaching toward the cosmos had begun. And it all started with images that almost remained hidden. A reminder that the greatest discoveries only matter if they're shared, that truth belongs not to institutions but everyone, and that sometimes the most significant frontier is in space itself. But our willingness to face what we find there, together, the darkness had lifted. The real journey was just beginning.